did mention to a couple of students about the format of the exams that are coming up, but not in front of everybody. So here's what you're going to get. The test will be in two halves. The first half is multiple choice questions. Probably, I think we could probably live with 25 or so multiple choice questions. And then the rest of it would be calculations or theoretical explanations. And for kinetics, it's going to be all calculations. So the multiple choice questions are going to be of the same style that are on the chapter quizzes. So that would be 13.2 and 14.2 that are currently up on Blackboard, soon to be joined by 15.2. I sourced those from material that comes with the textbook. I don't like the way that they're written, but they're all written the same way. They're all written poorly. But they work and they cover the material. Okay. Then there will be questions in which you will have to show all of your work. And we're going to run through, so that's what these are going to be, more the style of the written questions. And these are going to be a combination of questions that I make up myself and questions that come from the textbook. So it tells you at the top here. These are questions that I really suggest that you do from the textbook. And I picked a couple of them out, and we did one of them earlier on in lecture. Variations of those are going to be the things that I want you to know. Now, like for Thursday's lecture, we're going to do something on Thursday where we're going to look at the rate constant at two different temperatures. And the text does that, and it's got multiple questions on that in the book, but they're all asking from a point of view that I would never do. They've got multiple questions in the book that are, here are two different temperatures, solve and find me the activation energy, which in my mind is something that we would never ever do. What's much more useful is, here's a reaction at room temperature. How much faster would it go if you warmed it up to 50 degrees? That to me is much more useful. And there isn't an example of it in the text. There's one example of it in the back of the book in the questions. So when I disagree with the way that things are done like that in the book, I mean, we will spend time doing that on the board. So the stuff that comes in the second half of the test will be stuff that we do on the board and or stuff that comes out of the book, okay? And I have a study guide of multiple choice questions because I pull them all off a CD and then I put 10 or 15 of them onto the quiz, and the remaining 30 I'll give to you. And I'm not going to create any new multiple choice questions. They're all going to be sourced from that pool. Okay. So if you go through those, and then you tear it up and you go through them again, you should be solid. All right, let's run through a couple of these questions. If the question has a Q, it's one that I've invented. If it has a number, it comes from the book. And there are a couple of really dumb questions on here because they're fundamental. And I mean, I have learned not to be shocked at 22-year-old science majors who don't quite understand that if A times B equals C, that B equals C divided by A. Okay. Because it's chemistry, you shouldn't have to know algebra as well. But yeah, apparently you do. Okay. So, the first question is a question about solutions and dilution. And dilutions are things that students do wrong all the time. They are not difficult. They should not be difficult, but people do them wrong all the time. I wrote one on the quiz. Most of the ones that are in the book come at the question this way. If I have a 0.1 molar solution now, and I have 50 milliliters of it, what's going to be the concentration when I dilute it to 750 milliliters? Which is fine, it's a valid question, but who's ever really going to ask you that? Is somebody just going to give you a solution and go let you play with it and then figure out what the new concentration is? Bearing in mind that everything on the planet costs money. Okay? People are not going to give you chemicals just to play with. What they're much more likely to do is say, I have chemistry lab coming in tomorrow. I'm going to need 2 liters of a 0.15 molar solution of acid. Go make it. I tell you what I want. Oh, go look in the stockroom and you find out that we've got 2 molar concentrated acid. But I need 0.15. I need 2 liters of that. So given what you start with, go make what you're asked to make. That's a valid question. The book doesn't have too many of those, so I invented one. Let's read what it is that I said. All right. At the start, it says, you have 1.0 liters of a stock solution of 0.50 molar NaOCl. Anybody know what NaOCl is? One person in the room knows what it is. They don't know that they know what it is yet. And I'm not pointing any fingers at who it is that knows that, but one person in the room does know it. That's bleach. That's sodium hypochlorite, NaOCl solution. So I have 1 liter of 0.5 molar bleach and an empty 250 milliliter volumetric flask. We've removed all the glassware from this room. A volumetric flask looks like this. It has a stopper and it has a bulb at the bottom. And you fill all this up, and then there's a little thin line. And you fill it until the meniscus hits the line, and that tells you that it is exactly what the volume printed on the label is. And this one says 250 milliliters. That means I'm really very confident that I've just put 250 milliliters in it. That's a volumetric flask. So I have 1 liters of stock solution of 0.5 molar bleach and an empty 250 milliliter volumetric flask. I've been asked to make 250 milliliters of a 0.1 molar bleach solution. What volume of stock solution should you pipette into the volumetric flask before diluting it up to 250 milliliters? Okay? So we need to figure out what we've got at the beginning and what we've got at the end, and then do M1 V1 equals M2 V2. That's it. So what have I got at the beginning? At the beginning would be M1 and V1, and at the end would be M2 and V2. Do we know what any of these values are?
M1 is 0.5, right?
Yep. down. It's always safe, if you've got time, and this is not the SAT where you've only got 60 minutes to answer 60 questions. If you've got time, write a little table to yourself so that you can keep track of the numbers. All right, what is M2? Let's stick with the molarities. Pass through the question, read the question. What's my final molarity?
1.
If the final molarity is higher than the initial molarity, then the question is flawed. It's a bogus question. It's busted. Because what you'd have to do would be evaporate the solvent off. So at least that's valid. And then what are my volumes? V2 is 250 what? Okay, am I going to use milliliters? No, because this is in moles per liter. So 250 milliliters times, right, there's 1 liter for every 1,000 milliliters. I'm going to have that in liters. And then what is V1? Yeah, V1 is the missing number, but it says a liter in the question. That's the very first thing that's in the question. The very first number in the question is you have 1 liter of stock solution. That number's a red herring. It's in the question, but it's unnecessary. What it's telling you is you have an unlimited supply. You have more than you need. It's not part of the question. It's not part of the question. The question is, what volume do I pipette out of that stock solution? So don't be fooled to put that 1 liter in the question. All right, so M1 V1 equals M2 V2. What's the quantity I'm looking for? It's V1. So V1 equals, let's take the M1, cross it over, the equal sign drops to the bottom. All right, put the numbers in. So I purposefully changed that to liters. It's always the safe thing to do. I didn't need to, because the molarities are going to cancel each other out. The molarities cancel each other out, and this is in milliliters. Then my milliliters carry through, and my answer is in milliliters. It's safe to convert it into liters. It's a safe thing to do. So I have M2, 0.1 times 0.250 liters divided by 0.5. Okay. That molarity and that molarity cancel. My answer will be in liters. What's that number?
25.
Yeah. Okay, so if you'd have left this as 250 milliliters, it would have popped out at this end of the calculation as 50 milliliters, right? That would be 1 liter. That would be 500 milliliters. This is 50 milliliters. The next digit down would be 5. All right, so either way, keep them in or change it to liters and then understand what we've got. Oh, is that my correct answer? Is 0.05 the correct answer? Yes. Yeah. Well, I don't know, I have to go back and check. It is if it's the way I've written it down on the board, because no, it isn't. Because look, it says in the question, I hate this, don't you all hate this?
Same thing.
Oh, no, look, it says in the question, 0.1 molar, yeah, NaC, so there you go. That's my significant figures, limited to 1. Yeah, there you go. You should never really have to lose points on a test because you got the significant figures wrong after showing some kind of chemical knowledge. But don't show me a whole string of calculator numbers here. There's 1 digit of precision in the question. That means you only get 1 digit of precision in the answer. Okay, next. Oh, here you go. So, the book has a couple of Raoult's law questions, but it doesn't have very many questions about mixtures of volatile liquids. So I invented one. I think we're going to follow it up with one that is from the book, that is a non-volatile, which we didn't really talk about too much in class. Okay. So we're talking about vapor pressure. So when you talk about vapor pressure, you have to state a temperature. So at 25 degrees, I have a vapor pressure for acetone, CH3COCH3 equals 201, and then this curious unit of pressure that is millimeters of mercury. Are we all comfortable with what millimeters of mercury is? It's from a manometer reading. So you have a reservoir of mercury, and pressure, the gas presses down on that reservoir and sends the mercury, forces it up a thin tube, and that tube just has lines graded on it, millimeters. And the harder the gas presses, the further the mercury moves up the tube. And this is literally millimeters of mercury. And the higher this goes up, the higher that pressure is there. And they use mercury because it's not compressible. Mercury is a metal, and it's very dense. You can do it with inches of water. That's another manometer reading. But water compresses just a little bit. So when you press on it, it squeezes, and then you have to put this kind of conversion factor on it of you're not reading the true pressure out. Okay? So this tells me that the amount of pressure that this liquid is exerting is equal to 201 millimeters of mercury. If there's only one number in millimeters of mercury that you need to know, what would that number be? What's atmospheric pressure? Anybody remember that? It's 760 millimeters of mercury. So the pressure of the atmosphere pushing down right now on the top of your head is 760 millimeters of mercury. So the vapor pressure of acetone is 201, and the vapor pressure of chloroform, CHCO3, is 173. Okay. I'm going to take a flask or a container of some kind, and I'm gonna put 100 grams of acetone into it. And I'm going to put 100 grams of chloroform into it. And then I'm going to measure how much vapor pressure that mixture of two volatile liquids, these both evaporate very readily. Chloroform, you may have smelled. It's kind of nice. Puts you in a deep, deep, deep sleep. Unfortunately, too deep for anybody to use it like recreationally. Really bad idea. Because it knocks people out. I mean, really knocks people out so much that it's not predictable. Used to be used as a very early anesthetic, but it causes, you know, occasionally people stop breathing because it just puts them to sleep so deeply. Acetone, ladies, this is the stuff you use to take the nail polish off your nails. It evaporates right off your skin. So both of these, volatile. So it's going to exert a pressure above the liquid. Okay, let's measure what that is. And we're going to use this one. This was the diagram, we're going to use Ralph's law, that if I started with no acetone, so this would be acetone, out to 100% acetone, which would be 1.0. Then when I have pure acetone, I'm out here at 201. And when I have chloroform, just pure on this end, it would be 173. So I should have lines that go that way, and if my solution is behaving ideally, the mixture should have a vapor pressure that lies somewhere on this line. Only I don't know where on this line I'm supposed to be. That's what the question's for. Tells you in the question what the quantities of each material are. But we've got to turn grams into the number that I need. What's the number that I need that goes on this scale? That's X. X acetone. And X chloroform. And X stands for mole fraction. So I've got to turn my grams into mole fraction. How am I going to do that? I'm going to turn my grams into moles, and I'm going to turn my moles into mole fraction. Okay? So let's break this down. I got two things. I'm going to do them one at a time. Acetone. I need to find the number of moles. What's my formula for discovering the number of moles in a material? Moles equals mass divided by formula mass. Do we all remember what formula mass is? Formula mass is the sum of all of the atomic masses in the chemical formula in their relative amounts as established by the coefficients in the formula. So, what is my mass of acetone? It's in the question. It's 100 grams. What is my formula mass for acetone? Gives you the formula, and there's a periodic table. At some point, with just carbons, hydrogens, and oxygens, you shouldn't have to look at the table, because carbon is 12. How many carbons do I have? That's 3 12s. That's 36. You don't need to use your calculator. How many hydrogens do I have? 6. Hydrogen is 1. 6 times 1 is 6. 36 and 6 is 42. Plus an oxygen. How many oxygens is there?
1.
Just that 1. And oxygen is 16. Yeah, it's 15.994. Don't care. We'll get by without it. So 42, 52, 58. 100 grams divided by 58. What are the units for formula mass? Grams per mole. And the grams cancel, and the per mole that's dividing right here flips up to the top. And 100 divided by 58, going to be like 2 point something, but 1.8.
1.7.
Okay. Is that exactly?
No.
Okay. All right, let's do chloroform. Chloroform. Moles. Mass divided by formula mass. It's 100 grams. It's in the question. 100 grams of this, 100 grams of that. Does not mean equal amounts. 100 grams of acetone does not equal 100 grams of chloroform. They're different. They have different masses. Okay, in chloroform I have 1 carbon. I have 1 hydrogen. And I have 3 chlorines. Without looking at the periodic table, what's the atomic mass of chlorine? It's the one with the fractional number. It's the only one with the fractional number that you should know. It's 35 and a half. Okay, so 90, 105, 106 and a half, 107, 109 and a half, 119. Okay, so that is 100 divided by 119-ish, which equals, what's my number of moles? Almost 1. Okay. 4 moles. Okay. The mole fraction of acetone equals the number of moles of acetone divided by all the moles, number of moles of everything. So if I put 100 grams of acetone and 100 grams of chloroform into the flask, what I'm doing is I'm putting 0.17 moles of acetone and 0.84 moles of chloroform into the flask. You need to add those two numbers together and tell me what that is. This is my total number of moles. Okay? Mole fraction of any material is the number of its moles divided by the total number of moles. This is N total right here. Okay? So that gives me 1.7 divided by 2.5, which equals, it's about 2/3, isn't it?
0.68.
Okay. If you were untrusting, you should calculate the mole fraction of the chloroform, which would be the number of moles of the chloroform divided by the total number of moles, which would be the 0.84 divided by 2.5, and I'm going to go out on a limb and say it's 0.32, because when those two numbers add together, they should equal 1.00. This is a percentage, but instead of being out of 100, it's out of 1.00. Okay? Those numbers don't add up to be exactly 1. You've got a small calculator error. If they don't add up to be anywhere near 1, scrap your calculation. Just scrap it and do it again, because you've got a huge error in there somewhere. Okay, so I put 100 grams of each in that flask. Here's where I am. I'm 68% of the way on the black line and 32% of the way on the blue line. So right here, that's the number that I should be finding. Okay? Okay. In a two-component system where they're both exerting a partial pressure because they are both volatile, the pressure that I should be feeling is the mole fraction of component A times its pure vapor pressure, which was in the question, plus the vapor pressure of the mole fraction of part B times its pure vapor pressure. All right. A can be acetone, so this is 0.68 times the vapor pressure of acetone, 201, plus the mole fraction of chloroform times its pure vapor pressure, 173. So my 0.68 times 201 plus 0.32 times 173. And this will give me an answer that is in whichever units I use, because mole fraction doesn't have units. It's just a number, it's a relative number. It's like percentage, it doesn't have a number. It doesn't have units. So whatever units of pressure you use, they have to be the same. They could be pascals, it could be atmospheres, it could be millimeters of mercury. Whatever number that comes out to be. I don't know what it is, I just wrote the question. I may have written it down. Don't know what I did with that. Do we have a question? Do we have an answer?
192, 104.
Okay. 192 millimeters of mercury. All right, so I don't know if that's the right answer or not, but I can use a little bit of logic because it cannot be bigger than that number, and it cannot be smaller than that number. And it should be closer to this number than it is to that number. So I think that's right. I'm completely happy with that. Okay. What have I got? Chloroform and acetone. In real life, now we did talk about deviations. What are 2 deviations from Raoult's law? This is Raoult's law. In real life, this one is going to deviate that way. Because, do you remember what hydrogen bonds are? You should. Did we teach it? Yeah, we taught it in chapter like 11. Hydrogen bond. If hydrogen is directly attached to an electronegative atom, you're capable of making a hydrogen bond. So acetone can't do it, and chloroform can't do it. But in combination, they kind of half-heartedly do it to each other. That the hydrogen on the carbon is kind of primed to set up a hydrogen bond, and the oxygen with its lone pair of electrons is kind of set up to receive one. So there's gonna be an attraction between those 2 molecules, and I would fully expect that if I tried to measure this experimentally, I would come in under what the theoretical number is supposed to be. Okay. All right, I'm going to skip over the next 2 questions because question 1358 from the textbook does all of this again, but there's a word in the question that makes it completely different. Question 1358 says ethylene glycol. Real name is 1,2-ethane diol. It's an alcohol. It's 2 alcohols stuck on 2 carbons. That is a non-volatile liquid that we use in antifreeze. The vapor pressure of pure water at 60 degrees is 149 millimeters of mercury. A solution contains a 1-to-1 mole ratio, so you don't have to find the number of moles and then find the number of mole fractions, right? So it's 1-to-1 mole ratio of ethylene glycol to water. The vapor pressure of this mixture is 67 millimeters of mercury. Okay. A goes in, B goes in. Okay? A is going to be water. B is going to be the diol or the glycol. Now, A exerts a pressure. It tells you in the question that it's 100 and what? 149. So the vapor pressure of water is 149 millimeters of mercury. What's the vapor pressure of the ethylene glycol?
67.
That's the mixture. That's the vapor pressure of the mixture. What's the vapor pressure of the ethylene glycol? It says it in the question, but your brain's probably skipped over it. It describes ethylene glycol as being non-volatile. It has a vapor pressure of nothing. 0. Okay? So at this point, I no longer am interested in B's chemical identity. B just became an obstruction. This is B. It's going to be 50%, or 0.5 by mole ratio, by mole fraction, 50% of the contents of the container, which means 50% of the surface of this liquid. The rest of the liquid surface is water. And it's only the water that is now exerting vapor pressure. So, P total equals the mole fraction of A times the PA, standard, plus the mole fraction of B times PB, standard. So this is the mole fraction of water, the vapor pressure of water, plus the mole fraction, I'll call this glycol, of the glycol, times the pressure of the glycol. So this tells you that they're in a 1-to-1 ratio, molar ratio. So half of the moles that are in that solution are water. The mole fraction of water is 0.5 times its pure vapor pressure, 149, plus half of the molecules of the glycol, they're my black dots, times its vapor pressure, which is 0. What is 0.5 times 0? 0. That whole term just disappeared. So 0.5 times 149 equals 74.5. Okay, P total, the vapor pressure of this mixture should be 74.5. It isn't. The question tells you when they measured it, it was 67. Can we live with that number? It happened, it's real, it's in the question. Is that a positive or a negative deviation from Raoult's law? The number is less the experimental. So if I find my experiment is 67 millimeters of mercury, my finding is that my experiment is less than the math predicts. This is a negative deviation. This means the molecules are sticking together. And yeah, they're going to stick together. because this can hydrogen bond for real, and that can hydrogen bond, so those molecules are going to stick together, only this one doesn't escape because it has no pressure. Okay. So this is really preventing the water from getting out of that solution. That's why the number's a little bit low. Okay? A couple of other questions on this page. One says, what is the concentration of pure water? How would you go about answering that question? Concentration, what would my units be for concentration? Molarity, which is moles per liter, okay? So I'm asking what the concentration of pure water is. My answer is going to be in moles per liter. So all I have to do is figure out how to adjust that. If I had a liter of water, I need to know how many moles of water that is. In order to find out how many moles I have, I need to know what the mass is. What is the mass of a liter of water? How much does a liter of water weigh?
18 grams per mole.
Yeah, that's what we're going to hit next. But right now I'm just going volume to mass ratio, and then we're going to do mass to moles ratio. So a liter of water weighs 1 kilogram. It actually weighs 998 grams. It's a little bit off. It's like 997 point something. It's a kilogram, which is 1,000 grams. Okay, so if I have a liter of water, I have 1,000 grams of water molecules. Formulae I need. Moles is mass divided by formula mass. Molarity is moles per liter. Okay? I know mass. 1 liter of water is going to contain 1,000 grams. Put 1,000 in here. Oops. What's the formula mass of water? We just said it out loud a second ago. 18 grams per mole. There's 2 hydrogens, each at 1, and an oxygen at 16 is 18 grams per mole. A 1,000 divided by 18 equals 55.5, yeah? Okay. So 1,000 grams is equal to 55.5 moles, and my molarity is number of moles per liter, and my number of liters is 1. There are 55 moles of water. in every litre. That's a lot. That's a big number. 1339. What is the molality of 4.8 grams of salt in 0.35 litres of water? Oh, there you go, there's a density. Density of water is 0.997 grams per milliliter. Okay, let's do that one. So this is 13, who? 39. Okay, you didn't read this, misread this. It is not molarity, it is molality. The question gives you a mass and a volume. Molarity would be moles per volume. So you would convert the mass into moles and divide by that volume. That's not what we're asking you to do. We're asking you for molality, which is moles per kilogram. So I've got to convert my mass into moles, and I've got to convert my volume into mass. 4.8 grams of sodium chloride in 0.350 liters. Of water. And the density of water at this particular temperature, because you have to quote it, is 0.997 grams per milliliter. Okay, so you got to convert the mass into moles. Well, moles is mass divided by formula mass. Mass goes on the top, that's 4.8, and formula mass goes on the bottom. Sodium is 23, yeah, 22.989, I'll live with 23. And then chlorine is 35.5. So what's that? 58? 58.5. That gives me a number. And this is grams, and that is grams per mole. So once again, the grams cancel, and the per mole now goes to the top. We do have 3 digits of precision, so let's keep it in. Okay, so now, here we know. Density is mass per volume. So if density is mass per volume, and my question gives me volume and density and leaves mass as being the number that I have to find, because my molality is the number of moles per kilogram. If D equals M over V, what is M? V has to cross the equal sign. Goes this way. Okay? If you write your units in, then the units will, if they cancel out correctly, then it will lead you to the correct answer. So mass needs to be in grams. Density is in grams per milliliter. volume is currently in milliliters, right? So let's figure this out. Mass is, what's my density? 0.997 grams per milliliter times the volume. Oh, volume's in liters. But my density is in grams per milliliter. So I have a choice. I do one of two things. One of two things. I either change my liters into milliliters, or I change the density to read in liters. And we talked about this. What is the conversion factor if instead of saying grams per milliliter, I wanted to say kilograms per liter? What is that conversion factor?
1.
It's 1, because it's 1,000 grams is a kilogram and 1,000 milliliters is a liter. Rather than change your volume to match the units of your density, just switch out the units of your density. It's now kilograms per liter. I didn't have to change the number because it's the same number. All right. The liters will cancel and it will give me an answer in kilograms. Which is useful. So 0.997 times 0.350 equals, can't be very far off from this. What's your answer? 0.349 kilograms. Okay, so the molality is that number divided by that number. Whatever that comes out to be. What was the number?
0.235 kilograms.
Point.
235.
There you go. Okay. All right. That's everything that you're ever going to need to know about Chapter 13. The cool part in there is mixing making binary mixtures of volatile liquids and predicting what the pressure is. There's a couple of Henry's law questions in the book, and I have relegated them to the multiple choice part of the test because yes, it's real that the pressure above the surface of a liquid is proportional to the amount of the gas that is solvated inside the liquid, but that constants that you have to use is so picky that it's not going to have a wide application. Okay, dumb questions at the beginning of chapter 4, team. These are things that I need you to know and familiarize yourselves with. Formula for a straight line. It's the last thing that we wrote in lecture. It's y equals mx plus b. That is going to be a big deal in tomorrow's lecture. We're going to rearrange two different formulas to both fit y equals mx plus b, and we're going to use them in the case that the data gives us a straight line for whichever one of those scenarios it is. Okay, and then some of the stuff that we're going to do is a log scale, and you all need to understand what the magnitude of a log scale means. So at some point you should find out what the log of 1 is, and the log of 10 is, and the log of 100, and the log of 0.1 is. And just see, oh look, when the underlying number changes this much, the log changes this much. And it might actually reveal why logs were invented in the first place. So we have two sets, and you've got to familiarize yourself with how to use it on your own calculator, because I'm not going to be able to help you with, everybody got a different calculator. Log to the base 10 is spelled out log. The natural log that follows the exponential decay that we saw in class earlier today is ln. You need to know, what is the ln of 1? What's the natural log of 1? What is the natural log of 10? What is the natural log of 100? What is the natural log of 2? What is the natural log of 0.1? And what's the relationship between the log and the natural log? Because when you write them out, is there a clue to being able to interconvert between one and the other? That we won't do right now, but we will do later on. Okay? And then 1417, relate the rate of loss of reactant to the rate of gain of product. For nitrogen, plus 3 moles of hydrogen makes 2 moles of ammonia. We did 3 of those in class today. I'll let you fill that one in on your own. Okay, we did a few of those in class. Should have had time to let that sink in and be able to know that a loss is a negative number, and look at what the coefficient is in front of the molecule. Take that reciprocal. 14.3. You study the rate of reaction measuring both the concentration of reactant and the concentration of the product as a function of time, and obtain the following results. Oh, and then there's no question. I cut the question off. So it shows this. If I've cut the question off, I have to do it. You can't do it on your own. What does it show? It shows that over time, that happens. So the question's going to be, relate those changes in concentration over time and perhaps predict the stoichiometry of the reaction. What's really going on there? Is A a reactant or a product? I got amount here, and I've got time there. A is a product. Its concentration is growing over time. Is B a reactant or a product? B's concentration is decaying over time. What's the kind of stoichiometric relationship between B and A? I mean, it's kind of semi-quantitative. It's a graph. You might not know exact number, but you can kind of guess. This is my initial concentration right here of B. And then all the way up here, this is my final concentration of A. How does the concentration of A get to be higher than the concentration of B? When there's more of it. B is splitting apart and making 2 molecules of A. Okay, write that down in terms of, okay, relate the rate of loss of B to the rate of gain of A. B is being lost. This is a dissociation. 1 molecule of B is splitting apart and making 2 molecules of A. A is twice as much as B ever was. So we take that 2, because this is a gain as a plus, we take that 2 and put 1 over it. That the rate of loss of B is only half the rate of gain of A. Okay, 1430 is like one of the questions that we did in class. Following data were collected for NO2 picking up oxygen to make, NO picking up oxygen to make NO2. And I expect it's asking for a rate law and then perhaps something else. It looks like it's a little bit more detailed. This is 1430. I have a PDF copy of the 13th edition of the book, not the 10th edition. So I've scribbled over some of the numbers. Okay. 1, 2, 3. I have a concentration of NO. That's in moles per liter. I have some concentration of O2. And I have a rate. It goes 0.0126, 0.0252, 0.0252, I am not a fan of exponents that are not in multiples of 3. I see no need for this. I'm a fan of you being kilo, root quantity, milli, micro, nano, femto, right? I don't, 1.3 times 10 to the negative 1 is more confusing to read than 0.113. Okay, I see no need for this. Neither do I see a need for the negative 2. So this would be 0.0564 and 0.0141. Something that we did in England that we don't do in America is we write that first 0 down. Too many Americans are taught that is okay to say 0.113. No, there's really a 0 there. And the 0, see how many zeros there are? one of them? See how many zeros there are? There's two of them. And there's two of them there. That is 0.0141. That's a way that I was always taught to keep track of what the exponents really mean. Unfortunately, so many people just say, oh, 0.1. No, it's 0.1. Okay, I'm much happier having those numbers than having these numbers. Those numbers are ugly. All right, you should be able to do this. In fact, my feet hurt, my voice hurts, and really somebody else should do this for me. I'm sensing there are no volunteers. Your strategy needs to be find a scenario under which you can keep one of those quantities constant and do something recognizable to the other quantity. Ideally, you should be doubling it, because that's easy for our human brains to understand. And then you need to find a second scenario under which you keep the other quantity constant, and you alter the first one, and you look at what the rate. Look at my handwriting is getting all sloppy now. I'm tired. Okay. So, in 1 and 2, experiment 1 and experiment 2, this column remains constant. So the values for row 2 remain constant. The values in row 2 are higher than the values in row 1, so it's honestly easier for our human brains to understand the big number divided by the little number. It's a little bit more difficult for us to think about fractions than it is about whole numbers. You learn whole numbers before kindergarten. You learn fractions in what grade? I don't know. But later, right? Because they're more difficult. So, I'm going to take line 2, and I'm going to divide it by line 1. And that's going to give me 0.0252 divided by 0.0126, which to my eyes looks like it's doubled. And then in the O2 column, I have 0.0125 divided by 0.0125, which is constant, which is what I want. And then in terms of rate, I have 5.64. No, I'm not going to do that. I told myself I wasn't going to do it. 0.0564 divided by 0.0141. Now, I don't know what that is, but it's not doubled, because 0.0141, when you double it, is 0.0282. But 2/28 is 56. So that's times 4. Okay, I have doubled the concentration and found a 4 times increase in rate. What does that mean? That's second order. Okay, which 2 rows am I going to use for the next experiment? These 2 to be constant, and this one is bigger than that one, so 3 on top of 2. So 3 on top of 2 puts these two numbers together, and that's my constant. Don't go having two variables moving at the same time. It's impenetrable at that point. And then 3 over 2. Put the big number on top. That's a doubling. Doublings are easy to understand. And then that leaves me, this is the number that goes on the top, 0.113 divided by 0.0564. That looks like it doubled. When I double the concentration, I double the rate. That means that this reaction is first order with respect to, so this would be for oxygen, and the first one would be for nitrogen and monoxide. Okay? So rate law reads rate equals K NO and then O2. And the NO, when you doubled it, made the rate go up by 4. So the reaction is second order in nitrogen monoxide and first order in oxygen. So that rate is third order. You add the individual orders together. Okay, let's see what the follow-up questions are. What is the rate law? What are the units of the rate constant? Ooh, okay. Tell me what the units of the rate constant are. What is the average value of the rate constant calculated from 3 data sets? Okay. What is the rate of disappearance of NO when NO is 0.75 and O2 is 0.1? Okay. So K is rate divided by the concentration of NO squared, which in turn is multiplied by the concentration of O2. And that is molarity per second divided by molarity times molarity times molarity. This first molarity cancels out. Molarity divided by molarity. But that then leaves me 2 molarities on the bottom. So the units for this rate constant, for this particular reaction, and the rate constants for a third order, we've not seen one of these up until now, is molarity to the -2 seconds to the -1. All right. I was never a fan. What are we doing for time? I was never a particular fan of doing that exercise. The next part of the question says, find the average value of the rate constant. So what you would do is you would rewrite the equation this way. K equals rate divided by this concentration squared divided by that concentration. And then use those numbers in it to find you a new column with K in it, and then another, and then do it again with these numbers, and then do it again with these numbers, and then take the average. Okay, it would be something that we might do in lab, but it's not something that I really think I need you to do on an exam. You do it in lab, and you find out, hey, that number is constant-ish within experimental error. Okay, I don't think I need you to do that in lecture. But what about the next part? What is the rate of disappearance? This is 1430. Let me take a look and see if I want to do this. And then the remaining questions we haven't got to yet in class. And I'm losing my voice and my feet hurt. No, that's the wrong chapter. Okay. So we'll do this one and then we'll be done. So, you were given this experimental information. Wait, what am I going to do? Okay. That information is given to you experimentally. Once you find the rate law, you can find the value of K, all right? And once you find K, then you can invent concentrations without doing the experiment. I can say, I wonder how quickly this reaction would go at these completely made up concentrations. But I found out what the value of K is, and therefore I can do that. Okay, so let's do that. We're going to find the value of K, and then we're going to find the rate at some completely new concentrations. It says 0.75 and 0.01. Okay, so these concentrations are not in my experimental table. But once I solve for the value of K, that's like knowing what the line is. That's my constant. It ties everything together. Now I can just pump any number into that. So let's find the value of K. Let's pick one. All right. Typically, you don't want to take the number. The smaller the concentrations are, the more likely you are to have an experimental error. So if I take this one, that has the biggest numbers, right? That's probably going to be the best bet. So I'm going to take line 3. I'm going to take the values from line 3, and I've rewritten that K is equal to the rate divided by NO squared O2. Okay, so on line 3, the rate was 0.113. and O was 0.252 squared times 0.025. Okay. That will give you a value for K. And then I can find the rate at some completely new number, because the rate equals K and O squared O2 0.75 squared times 0.01. So let's find this value of K. Do we have a number? I don't know what it is. I might be able to find it. 7.1. Nope. Which one did I do? 0.113. 7.12 times 10 to the 3. Once you find the value of K, you can put it back into the rate law and find values of the rate for experiments that you just dream up in your head. So 7.12 times 10 to the 3 times whatever the square of 0.75 is times 0.01. That's a number. That number should be in the ballpark of 1.42 molarity per second. Okay. All right, I'm about done. There's a little bit more on the worksheet, but we haven't covered it in lecture yet, and you only got the sheet today. I only posted it at 2 o'clock in the morning. So hang on to it for a couple of days. I'll take it back from you Thursday, okay? And then this will be graded. So this will be kind of the way it goes. Then there'll be another, we'll do another one on Monday. We'll do some temperature change things or something else, kinetics. That there will be questions. I will expect you to prepare for them. We'll run through what they are. It's like you doing your homework in the classroom. Okay? It works for me. I don't want to talk anymore. I think I have one cough drop in my bag. You may go.